Hi, everyone, and welcome to Topological Data Analysis and Neuroscience. So in this week's videos, we'll be talking about multi-parameter persistent homology. Right, so pretty much what we've meant so far in this course when we've said multi-parameter persistent homology, when we've said just persistent homology so far in this course has been what could also be known as one-parameter persistence. And the reason it's one parameter is because all of our filtrations we've looked at so far have one parameter defining the filtration, right? So if we look at the V-torus-Rips filtration, there's a single scale parameter that induces the filtration there. So that's what makes those one parameter filtrations. And in one parameter persistence, the story is very nice. As we've seen, the algebraic decomposition theorem tells us that one parameter, the homology of one parameter filtrations breaks down very nicely into just births and deaths. That's all. With multi-parameter persistence, though, the story is much more complicated. Right, so with multi-parameter persistence, right, so with one parameter persistence, all of our filtrations are indexed by like a sort of linear set. We can think of them as, and we can view this as, right, it's an ordered set. This is indexed by the real number line. Right, for the V-torus-Rips filtration, we have a simplicial complex for each real number. Now with multi-parameter filtrations, though, what we're going to get is they're not going to be indexed by the reals anymore, but they're going to be indexed by r to the n, where n is some integer. So it could be 2 or 3 or whatever. And so now when we look at these filtrations, the story is much, much more complicated. Persistence modules don't break down nicely as a direct sum anymore, at least not as a direct sum into nice things like they did in the one parameter case. But even though, okay, so the story is not as nice here, but there's still some stuff we can do. We can still glean information from these multi-parameter persistence modules, and they are useful for applications and neuroscience as well. Okay, so let's look at multi-parameter filtration. So here on the right is an example of a multi-parameter filtration. This is a 2-parameter filtration here. And what we're looking at here, this is a filtration of a set where of a data set where on the y-axis we're filtering by radius. So you can think about this as the normal V-torus-Rips parameter here. If on the y-axis it's just the usual V-torus-Rips parameter. Right, we're sort of growing balls around each point in the data set. But on the right, we're filtering by curvature, or sorry, on the x-axis, we're filtering by curvature here. So what we're really doing is we're saying we only want points in our data set that are, in some sense, not too curvy. And as we increase this curvature parameter, we're allowing more and more points into our data set. And if we combine these two things, we get a multi-parameter filtration. Okay, so formally, what a multi-parameter filtration is it's a, right, it consists of a topological space. Oftentimes, for us, this will usually be a simplicial complex for each a in r to the n. And whenever we have a real number less than or equal to, or sorry, really, this is a vector. These are vectors a and b in r to the n. If a is less than or equal to b, meaning all of the components of a are less than or equal to all of the components of b, then we need an inclusion of the topological space at a into the topological space at b. So this is almost exactly the same definition of a one-parameter filtration that we looked at before, except now, the only real difference here is that A and B are in R to the N, not just the reals. And we're using the product order on R to the N rather than just the, well, there's sort of one natural order on the real line. Okay, and so these multi-parameter filtrations arise in practice quite frequently. So there's three main examples we'll see. The first one is our augmented metric spaces. So these are just metric spaces with real valued functions on them. So this example on the right is an example of an augmented metric space. We have this metric, which gives us the scale parameter. So we can do a sort of v-torus Rips thing on it. But then we also have a function on this metric space as well, which is the curvature function. And we can filter by that as well as the radius. And so we get two parameters here. Another example are sub-level set filtrations. So we've seen these before with real valued functions from, say, a topological space to the real line that induces a sub-level set filtration. What we'll see with multi-parameter persistence, we'll get sub-level set filtrations whenever we have a function from x to not just the real line, but r to the n for any n. So it's a more general setup. And then lastly, we'll look at level set filtrations as well. So we'll go into more detail on that later on. Okay, so first things first, let's take a look at sub-level set filtrations. So just like in the one parameter case, if we had a topological space or a simplicial complex, and we have a function from that space into, so before we would always look at functions into the reals. Now we're used in the multi-parameter case, so we can look at functions into r to the n. We have these extra parameters here. So any such function is going to induce an n parameter filtration. We'll call it M, and it's defined by this formula. It's pretty much the exact same formula. We just look at everything that maps to something at or below A. So for example, if our space X is this annulus right here, and let's say our function into R2 is, well, I already have this drawn as a two-dimensional thing. So just imagine your computer screen as R2. Okay, and so let's say we pick a point A. So here we have this point A, and then we want to look at the sub-level set of A. So the sub-level set is everything that maps at or below A. So in this picture, it would be roughly the this lower left quadrant of this circle right here. Okay, so yeah, so sub-level set filtrations are pretty much the easiest example of multi-parameter filtrations. But let's move on to augmented metric spaces now, because these are possibly the most important example in multi-parameter persistence. So these augmented metric spaces, right? We've seen metric spaces before, and these are just metric spaces, except we also have a function on our on the point set of the metric space, right? So we have this set of points x, and we just want a function from x to the reals. That's it. Yeah, so now what we can do is let's pick a real number. We'll call it sigma, and we'll define x sigma to be the set of everything that maps to something less than or equal to sigma. So this is also just the sub-level set of sigma along fx here. So, right, we're basically just taking a subset of our metric space, and right, we want to look at just the set of all the points in our metric space such that our function has below some value on those points. And now we can use this to define the Rips bifiltration on this augmented metric space. And this is just going to be the epsilon Rips, right? So this is just the epsilon Rips complex of x sigma. So we have two parameters here. We have epsilon and sigma. And right, basically what we're doing is as sigma moves, we're taking, as sigma increases, we're taking more and more of the vertices from x into our set that we're considering. And as epsilon moves, we're adding in more and more simplices between those vertices. And so it's a sort of combination of these two things, right? So in the one axis, And in fact, maybe let's just go back to a picture. So this here is an example of a RIPS bifiltration, this picture right here. So in this example here, our function fx is the curvature function. And so if we just look at this bottom row right here and look at what happens as we increase the curvature parameter, we're not actually we're not growing the balls around the points any bigger. Instead, we're just including more and more of the points from our metric space into the picture. But if we look at what happens, let's look at the left column now. We're working with the same the same points in each part of this column, but we're growing the balls around each bigger. So you can think about these RIPS bifiltrations as a combination. It's a filtration incorporating both curvature and radius here. And so these are very useful in practice. I mean, we saw that example with curvature, and that can actually help a lot to study data sets, and has been used in practice before, is considering a bifiltration where you're filtering by both radius and curvature. Another example that's been used frequently is filtering by radius and density as an attempt to make persistence more robust to outliers. And so this is one of the big problems with ordinary one-parameter persistence, is that persistent homology is very susceptible to outliers. So now you might be thinking, well, we know there's the bottleneck stability theorem that says that persistence diagrams are stable, so they shouldn't be too susceptible to outliers. Now, the issue with that is that outliers actually change with the metrics we're working with. Outliers change the input quite a lot. So that will it won't break stability. Stability still holds, but it's just that if the input is changed by quite a lot, stability says that the output could also be changed by quite a lot as well. And so that's an issue with persistence, is that if your data set has outliers, then it might give you something that's not very interpretable. And so the common way to address this is to incorporate a density function into the filtration. So if we look at this picture here, so what we have here is we have 3 data sets. So X is this data set on the left, and this is points that are sampled from a circle with some noise. And we can look at the barcode here. The barcode for one-dimensional persistence is telling us essentially that we have one hole, right? We have this one homological feature that is very long-lived. It persists for a very long time. So that's telling us that we have this one big hole, and it's very unlikely to be just noise. It's a very robust hole. And then we have a bunch of very short-lived holes, which we can think of as just noise in this case. Okay, now if we move to Y, so Y is this data set in the middle, and it looks like a data set. In fact, it's pretty much exactly the same as X, except with some outliers now in the middle. And just looking at this, we can sort of tell it looks like it was sampled from a circle with some noise, but with some outliers in the middle as well. And sort of our eyes can detect that, but unfortunately, persistence can't really detect that at all, because those outliers in the middle are highly affecting the persistence diagram. And we can see the barcode here. It doesn't have any long-lived bars at all. And if you imagine, right, if we imagine what the V-torus RIPS complex is doing, right, imagine growing balls around each one of those points. In the data set on the left, we're going to see that big hole, and we're going to see it last for a long time. But in this data set in the middle, we're not going to see a big hole at all, right? As we grow balls around all of the points at once, the middle is going to fill in pretty quickly, because the middle is already mostly filled in. And so what we're seeing in the barcode for Y is we're not getting any long bars at all. So we're not really able to tell if what we're seeing is noise or not. And finally, in the barcode for Z, here Z is just is pretty much a randomly sampled points here. And in fact, the longest bar in the barcode for Z is roughly the same as the longest bar in the barcode for Y. So the barcodes are not really able to tell these two data sets apart here, even though with our eyes, we can sort of see that Y looks like it should be a circle with some noise. The persistence diagrams can't tell us that. And so this is why we want to incorporate a density parameter into filtrations. Right, and so one way we can do this is just with augmented metric spaces, right? So if our function fx is a function capturing density, then we can use this RIPS by filtration here and get a multi-parameter filtration that incorporates both density and scale parameter. And so we can sort of fix this issue. Okay, so just like in the 1D setting, right, when we had persistence, right, we started with filtrations, we applied homology to filtrations to get persistence modules. We can do the same thing in the multi-parameter case. Okay, so right, we started out with multi-parameter filtrations, which we had a topological space or a simplicial complex at each point in R to the n. And then we had an inclusion from the space at A to the space at B, whenever A is less than or equal to B. So applying homology to that, well, we started with a topological space at each A. So now we're going to have a vector space at each A. And we started with an inclusion, so a simplicial map or a continuous map from the space at A to the space at B. Homology is going to turn that into a linear transformation from the vector space at A to the vector space at B, whenever A is less than or equal to B. Right, and so yeah, we get this just by applying homology, and we can pick whichever dimension we want. So for example, here, let's look at this, this 2-parameter filtration on the left. Right, so this is a filtration of this triangle right here. And basically what we're going to do is we're going to apply 0-dimensional homology to this. So we're essentially just counting connected components here. And what we get is we get a vector space for each point in this grid, and we get a linear map whenever a point is less than or equal to another point. So this right here on the right is what a multi-parameter persistence module looks like. It's basically just a sequence of vector spaces with linear maps in between them. Except now they're arranged in for 2-parameter persistence, you can oftentimes think of them as being arranged in grids. Same thing with higher dimensions as well. So it's a bit more complicated than just the linear case where everything is 1-dimensional. Okay, so right, with 1-parameter persistence, we had this notion of metric between persistence module, which was called the interleaving distance. And we're going to have the same thing here. We can define the interleaving distance between multi-parameter persistence modules now, and it's roughly the same definition. Okay, so before we worked with epsilon interleavings, where epsilon was just a real number. We're still going to have epsilon interleavings where epsilon is a real number. But now we're basically going to be shifting by epsilon, not just in one direction, but in all directions at once now. So we're going to do this using this vector epsilon, where this is just epsilon in each coordinate. Okay, so an epsilon interleaving between 2 persistence modules M and N is just a bunch of linear maps, right? And so you should think about this as being roughly the same as what we looked at in the 1-parameter case, only now we're working with vectors rather than just real numbers. These are vectors in Euclidean space, but everything else is pretty much the same, right? So we need maps from M of A to N of A plus epsilon, and from N of A to M of A plus epsilon for each A. And we need these maps to be such that these diagrams commute. So these diagrams are pretty much the same diagrams we saw in the 1D case, right? And so, yeah, or we're not going to go over these diagrams. We're not going to spend too much time on the interleaving distance here. But the moral of the story is that we can define a distance on multi-parameter persistence modules in roughly the same way that we could on one-parameter persistence modules. Okay, so with one-parameter persistence, we had this great structure theorem, right? The algebraic decomposition theorem, which said that every persistence module broke down into a direct sum of interval decomposable persistence modules. So it would be great if we could have, or sorry, every persistence module breaks down into a direct sum of interval modules. It would be great if we could have the same thing in multi-parameter persistence, right? Where we have every multi-parameter persistence module breaks down into a nice, simple decomposition of some basic building blocks. So let's try to define what these building blocks should be. So we're going to say a subset of R to the N is an interval if we have these two conditions here. So this first condition here is can be thought of as sort of the usual interval condition in the reals, right? If we have any 2 points in our interval, then we need to have every point in between those 2 points also in our interval. So this can also be thought of as convexity. The second condition is a connectedness condition. Now in the one parameter case, this is not necessary. It's implied by the first condition, but in the multi-parameter case, they are no longer equivalent. Or this condition is actually needed to ensure that intervals are connected. And so what we want here is basically that if we pick any 2 points in our interval, we can find a string of, basically we can find a zigzag getting from one point to another while staying entirely inside the interval. So the second condition is really just saying that our intervals are connected. Okay, and now that we have intervals defined, we can define interval persistence modules in much the same way that we defined interval persistence modules for one parameter persistence. Right, so these are just going to be persistence modules that are K on our interval and 0 everywhere else, and with all of the maps in between copies of K as the identity. So, right, if we look at this interval on the right here, this blue boxy thing, the interval persistence module for this would just be K if we're in this blue part and 0 everywhere else, with all the maps between K being identity maps. Okay, so we can now say that a persistence module is interval decomposable if it breaks down as a direct sum of interval modules for some multi-set of intervals. So this would be the goal, right? This is what we have in the 1D case, is that every persistence module is interval decomposable. They all break down very nicely, and we can work with those pieces, and those pieces give us the barcode. Unfortunately, though, this is not the case in multi-parameter persistence. Not every multi-parameter persistence module is interval decomposable. So here's an example, right? So here we have, and you can think about this as just being embedded in R2 if you want. So really, we're only just going to look at these 4 vector spaces here. And so, yeah, this example right here is quite nasty because it resists many attempts to decompose it nicely because, well, frankly, it just doesn't decompose nicely. And you can try, but it's not going to, it won't pull apart. There's sort of 2 parts here, but they're both intertwined which is something that you can't have in the 1D case, but is possible here in multi-parameters. Okay, so we can't decompose multi-parameter persistence modules nicely always, but maybe there's some subclass of multi-parameter persistence modules that we can decompose. And that's the main subclass of multi-parameter persistence modules that we can decompose are given by zigzag persistence modules. Okay, so a zigzag persistence module is just a persistence module of this form where, right, these two-headed arrows, these are not saying that we have maps in both directions between like V1 and V2. This is saying that we have a map in either direction. Pick one, but not both, right? We don't want maps going both ways, right? So this map F1, it could either be going from V1 to V2, or it could be going from V2 to V1, but not both. Yeah, and so all of these maps could be going in the same direction, which would just be one parameter persistence, or they could be like sort of alternating, which is usually the way people think of zigzag persistence, and why it's sort of called zigzag persistence is that right, you sort of think about it as a zigzag where it's like going up and down like that. And now these zigzag persistence modules, though, these do decompose nicely in the same way that one parameter persistence modules do. Oops. And so this is a very nice thing. And there's software for computing persistence diagrams or barcodes for these zigzag persistence modules. And I believe we'll look at some of those with like Dionysus and things like that. Okay, so let's look at an example where zigzag persistence comes into play from geometric data. Okay, so let's say we have, right, our setup is the same as we normally use for sub-level set persistence. So we have a function from a topological space X to the real line. So we're going to look at this example on the right here. So we have this topological space sitting above the real line, and the function we're looking at is just the projection function. So we're taking every point on the space and just mapping it straight down to the point beneath it on the real line. Okay, so normally to get a filtration here, we would look at sub-level sets, right? So if we wanted to look at the sub-level set at S2, we would look at everything that maps at or below S2. The idea with level set persistence, though, is that we're going to look at just the level set. So we're just going to look at everything that maps to S2 here, or for any T. We're just going to look at everything that maps to T. So for example, if we're looking at F inverse of S2, it's just going to be this middle circle here, gamma, the sort of waist of this shape. It's just going to be that one little thin one-dimensional circle and not this two-dimensional surface that we'd get if we looked at the sub-level set. Okay, so the idea here for working with level set persistence is that as T varies, there are only going to be finitely many places where the level sets change, right? Where the inverse images change homotopy type. So for example, like let's look at gamma, the sub-level set of, or not the sub-level set, the level set at S2, which is this circle gamma right here. And let's look at like what happens if we move S2 a bit. If we move S2 just a little bit, we still have a circle, right? It's just, maybe it's a little bigger, but it's still a circle. It's topologically the same thing. As we move it more, we still get a circle, and more, and we still get a circle, all the way until we hit A3. At A3, it changes. At A3, what we'll get is actually, it's actually sort of two circles, but pinched together at a single point. And then at right after A3, so for example, at S3, we'll also get something different. We'll get two circles that aren't pinched together at all. So just two disjoint circles. And then it'll change more and more as we move on. But the whole point is that assuming our function is nice enough, there are only going to be finitely many points where these level sets change homotopy type. So we'll call these points critical points. Okay, and so in this picture here, the critical points are given by the A1, A2, A3, A4, and A5. Those are the points at which our level sets change homotopy type. And so what we're going to do for sublevel set persistence is we're going to take our critical points, and then we're going to pick points in between each of those critical points. So our critical points are the A's, A1, A2, A3, etc. And then we're going to pick points in between each of those. So we're going to pick S1 in between A1 and A2, S2 in between A2 and A3, S3 in between A3 and A4, and so on. And what we'll get is this zigzag of inclusions of topological spaces, right? So we'll get a map from the sublevel set at S0 into, or sorry, not the sublevel set. We'll get a map from the level set at S0 into the inverse image of the interval from S0 to S1, right? Because S0 belongs to the interval between S0 and S1. Certainly the sublevel set at S0, or the level set at S0 will include into the inverse image of the interval from S0 to S1. Same thing with S1. The level set at S1 will include into that interval as well. But now the level set at S1 will also include into the interval between the inverse image of the interval from S1 to S2, and so on. And so what we'll get is the zigzag of topological spaces. And we can apply homology to the sequence now, and we'll get a zigzag of vector spaces and linear maps between them. And so we get a zigzag persistence module. Right, and yeah, so and because of that theorem on the last slide, or well, not really a theorem, but that result on the last slide, that we can decompose these zigzag modules nicely in much the same way that we would one parameter persistence modules. That tells us that actually we can study this quite carefully. We're not going to go too into the details here, but it's an active area of research and pretty cool concept.